Okay, moving on to our next presentation from Ugo Varetto, who's the CTO of the Pawsey Supercomputing Research Center.
Okay, thank you. I'm supposed to be talking about Setonix. I do not know what the audience understood from the title. I certainly did not come up with the title myself, but we wanted to play on the Australian identity of the new system because we're all excited and we never had anything this powerful deployed here, right? So that's where the title is coming from. So in this presentation, we're going to talk about the new supercomputer recently acquired. This is the agenda. Given the time constraints, I will have to quickly go through some of the material. Also because I wanted to address in my presentation some of the points made by the other speakers in their talks. And again, if you need more information, please feel free to just ask a question. So I'll start talking about what we do at Pawsey. I'll then discuss the requirements we looked at when going through the procurement process. And then I will be giving details on the new system, finishing up with a description of some of the extreme scale projects we plan to support. Pawsey Supercomputing Center, originally created to support mainly radio astronomy initiatives. We evolved over time to support about 200 research projects, more than 40 research institutions, and many scientific fields. And we also contribute to training and educational programs. In fact, we do have staff appointed as adjunct professors at universities where we deliver lectures and help in organizing educational activities. Given our involvement in the Square Kilometre Array and its precursor projects, we do have clearly a strong focus on radio astronomy. We receive data from radio telescopes located in the desert about 600 kilometers away and generate data suitable for consumption by scientists. So this is a snapshot of the current IT infrastructure at Pawsey with all the separate systems connected to a mostly 10 gig Ethernet network. We're currently operating several different file systems, namely Ceph, block, and object. We have Luster, CXFS, and GPFS. And the Galaxy and Magnus systems you see there are the ones we are currently replacing with the Setonix. So these are the requirements. In particular, I'm going to talk about how we translated scientific and operational requirements into high-level technical specifications, which ended up in our tender document. So these are the requirements coming from the scientific community. As most other centers, we need to support modeling, simulation, visualization, and data management services. We also support high throughput computing, machine learning, and real-time data processing. High throughput computing is mainly, but not only, bioinformatics, and real-time data processing is, in our case, the radio astronomy data processing pipelines. But in the future, we expect to be offering pretty much the same services, but at much larger scale and with more stringent latency requirements, talking about the data processing pipelines here. We also expect to be supporting more AI augmented scientific simulations. And in general, we anticipate seeing applications of machine learning to many HPC problems. And actually the previous presentations you have seen go exactly in these directions. I did put there some references. In fact, I did have references to both Alessandro and John's papers, which I removed because you just heard directly from them, and I put others instead. The reference there, they really cover from using machine learning for optimizing application performance to integrating AI with physical models. So these are the requirements. If you have questions, please feel free to ask. I wanted to spend some time on the FAIR principle. I don't have time for that. Again, if somebody wants to ask the question, happy to answer later. Okay, these are the requirements coming from operations in consultation with our stakeholders. And I tried to separate the requirements into two different categories: increase resource utilization and decrease cost. Increasing resource utilization and decreasing cost translates directly into increasing the return on investment. Yeah, again, I wasn't ready to go to some requirements in detail, but I'd rather move on. Let me just make 2 comments here. One is that we do have the requirement of running cooling infrastructure. We can ingest water at 21 degrees Celsius and pump it out at 30. This requirement comes from the fact that we pump water out of an underground aquifer. And another thing that came out when we analyzed the requirements is that we believe that all of them can be addressed by offering all services through a single software configurable system. So if you combine the previous requirements together, you get something like this, which pretty much reflects the content of our tender document. Also note that most of the requirements were actually expressed as preferences, because we wouldn't know what would be available, right, by the time the system would be deployed. Let me just make a couple of comments about some of these requirements. So because we want to support both operational and scientific workloads on the same system and maximize utilization, congestion control and quality of service are required. What we're doing now is actually distributing the workloads across different systems, because we cannot afford to have, say, an MPI all-to-all or all-gather operation from other applications affect the data processing pipelines. I'm also going to say that fast GPUs, and this was actually mentioned by Ben in his talk, do require a lot of memory near the chip, hence the high memory per flop ratio that I listed here. Is integration, that's where the Ethernet compatible requirement is coming from. But now let's have a look at Setonix itself. This is an actual picture I took myself of the first few cabinets we got. And this is just one slide about the procurement process. Note that we did not just procure one system, but had more than 10 procurements going on at the same time with dependencies on one another at some point. Here, the various reference groups acted as advisors and helped in validating the requirements and carrying on their evaluation tasks. We also got input from peer centers and research institutions around the world. In fact, Ben did share with us the first results they got on the MI50 GPUs at the time. And when it was still an option, we traveled to meet with various groups who were in the process of evaluating HPC technology, either as part of a research project or for their own procurements. So the entire process is going to take about 2 years when completed. And I put a picture here of contractors. These are actual contractors working on our floor. And they are preparing the floor for the new systems. Since one of the most challenging aspects has been really dealing with building works to accommodate a new compute and storage infrastructure. And it's been challenging because everything was based on projections and estimates. And we'll find out if we were right pretty soon, I guess. So this is Setonix. These are the technical details. You can read them for yourself. I did not put here all the information I had because the truth is that we won't know the actual details until the hardware is delivered. So for example, you might have seen online speculations about the capabilities of the AMD MI200 GPU. But those speculations are based on the MI100 GPU, right? And here we're talking about a completely different chip. This is a custom chip that is going to be integrated directly with the custom version of the Milan CPU. So I have no idea myself if this will be an actual product or we stay as an HPC only solution. Anyway, we'll have close to 3400 CPU chips and 768 GPUs, not listed here. We will also have some NVIDIA A40 GPUs for visualization purposes. 2 types of CPUs, Milan, and another one which is similar to Milan but supports Infinity Fabric connections with the GPUs. Next-gen GPUs with 128 gigabyte of HBM memory. These are multi-chip design GPUs. Interconnect, here we have on the list here 200 gig Ethernet compliant slingshot interconnect, but some of the nodes are connected at 400 gig, and the GPU nodes do have 800 gig injection bandwidth. Few words about Shasta, the Shasta system management software actually. So it implements a microservice architecture based on containers, similar, I would say, to say an OpenStack for HPC platform. We do have a lot of details about Shasta. In fact, I do have on my desk this 2 pound of paper manual, and there's a lot of stuff in it, but I'm not sure what I can disclose, so I'm gonna stop here. And more on Interconnect later. So let's move to the next slide. So here is where Setonix is going to fit in the center. As I mentioned before, the procurement process includes the acquisition of many other components, such as a 400 gig Ethernet backbone, a 100 gig firewall, object storage, and the new HSM environment. The tape picture you see there is really not just tape. There is currently a POSIX cache sitting in front of it, which will have to be replaced as well. And we are looking at moving all the services currently hosted on the other clusters on Setonix itself in the future, including the actual ingest nodes. But we'll need to make sure we can do that without any performance degradation. Okay, so when we procure the system, the 2 pieces of technology I was really excited about were cooling and interconnect. So I put here a couple of slides to explain why. So in the supercomputing system, the cooling infrastructure delivers cooled fluid directly to all the components which generate heat. And we believe that this is today one of the most efficient ways to cool off IT equipment, because you only cool what needs to be cooled. From these pictures, you can see that all the individual components, memory banks, network card, and the CPU are cooled independently through a sophisticated system of metal plates, microchannels, and independent liquid flow paths. You do not see here the GPU, because I do not have that picture, at least an updated one, but it's cooled in the same way. So the compute cabinets are cooled by a 22 degrees Celsius water loop, and the management and storage racks are cooled by a 16-degree loop using cooling doors. Interconnect, so interconnect topology is Dragonfly. So you have groups of fully connected nodes at different levels with the diameter of 3 hops. And the technology is based on slingshot, Ethernet compliant with built-in congestion control, not requiring manual configuration. It's implemented in hardware. Quality of service is supported through traffic classes. And okay, this slide is about congestion control and quality of service. The heat map and the diagrams are pretty self-explanatory. It's about the impact of network traffic on application performance. You can see that the ability to enable congestion control and the use of traffic class is beneficial in many situations. Figure 1 shows the performance of all reduce and all-to-all workloads running at the same time on a system in the same and in separate traffic classes, right? And the use of separate traffic classes greatly reduces congestion. Figure 2 shows the latency of trace packets sent between random pairs of nodes in the presence of congestion generated by random 10-to-1 traffic patterns. And the heat map shows the congestion impact of many applications. In one case, you can see right there that lamps experiences a slowdown of 17 times under heavy incast traffic. So incast is many packets sent to the packet, the port that requested the packets. And then, so I would really encourage everybody to have a look at the 2 papers I'm referencing here. Not so much because of Linkshot, but because of the methodology they use to analyze the problem and the strategies they employ to measure congestion in various scenarios, because it's important to analyze the impact on your own use cases. In many situations, you might not need congestion control at all. We're really looking at that because we want to support operations and science on the same system. And this is the GPU node. So I mentioned before that I wanted to address some of the points made by mainly John and Ben. And this is the place where I'm going to do that. So I cannot report the GPU information is on the tender response, but I can say that it will support matrix operations. No information so far about mixed precision, 32 or 64-bit. 32-bit is already supported on the MI100 for the matrix operations. In fact, the V_M_FMA opcode, I took it from the ISA specification from the MI100 card. But the most important aspect of it is that it will support cache coherence between GPU and CPU in hardware. So we won't have to go to the PCI bus anymore. I put here some C++ code written directly in the slide, which shows how today you would create a shared buffer and guarantee that all the right operations are performed before accessing the data. One is the kernel running on the GPU, and the other is a C++ thread. It's the CPU kernel and GPU kernel functions there. The thing is that with the bandwidth, this is going to be an order of magnitude higher than PCI Express 4 and low latency, and this cache coherence feature, right? I believe we'll be able to address what quite well what Ben mentioned when he said that they had to port. We had to port because it was at CSCS at the time that we had to port the code from Fortran to C++ just because of the copies, right? So in this case, the bandwidth would be so high that you should be able to share data easily between C++ and heap C++, right? So, and the other thing that John mentioned was the issue with I/O. So moving data from files into GPU memory. So once you have an architecture like this, right, you can, for example, map a file into shared GPU CPU memory and use the C++ code to read the file, then have a fence in the GPU code and wait for the data to become available, right? But all done very quickly through direct sharing of memory across GPU and CPU. So let me move to the next slide. Challenges. So system management. So the first challenge you see there has to do with the change in the way systems are managed. When you have microservice-based architectures with databases, message queues, ephemeral file systems, and containers, and the preferred way to interact with the system is by sending HTTP requests and parse JSON output, then sysadmins have to turn into DevOps software engineers, right? And move from using configuration files to develop code that interacts with the system through REST protocols. And in fact, our sysadmins are going to through the Shasta training this week. Workload management. So the second challenge is really about the integration of Slurm with containers and orchestrators. There is a question mark there. But it's not exactly like that, since we have looked at options like having separate partitions for standard HPC jobs and containerized ones. Shasta itself does provide this capability, actually. Application porting, you actually have already heard everything from Ben. Here is condensed in a few lines of text, but we do have a dozen or so of internal documents detailing what we've been experimenting with on Milan and the GPUs. Let me just mention that here we are really moving from multi-core to many-core on the CPU, because you go from 12 to 64 cores. And also, you need to be able to deal with the NUMA regions, right? We have seen a huge performance impact on some applications when changing the NUMA configuration on our Milan node, for example. GPU to GPU, we are talking about moving from CUDA and OpenCL to HIP and something else. To address that, we are looking at OpenMP, ROCm, meaning C++ and HIP, but also HIP, SQL, and libraries like Cocos. So far, moving from CUDA to HIP has been straightforward, just because the feature used by the CUDA codes we have seen were already supported by HIP. But I must say that not being able to map HIP / ROCm versions to CUDA versions is not really that easy to deal with. And also, of course, on HIP, I mentioned that here you do not have support for dynamic parallelism so far. I haven't checked the time. What is it?
It's about that time, Ugo, but if you're wrapping up.
I was just asking because I'm going to wrap up in 2 minutes, probably 3, so that's fine. Okay,
perfect.
Good. So just to mention the Pacer project, which actually Ben mentioned himself, very similar to Pascal. We selected a number of projects, and there I put a picture of the person who's running the program, Maciej Sitowski, our head of scientific services. Here, this is the list. Not going through all of the projects, but as you can see, we have a diverse mix of domains and international reach, also including industry in one case. And I really just selected 3 projects which are in line with the porting efforts I mentioned before. So Blink is a radioastronomy project where we are developing data processing and imaging pipelines using C++ and HIP. And the goal here is to go from hours of processing to real time. This one is a fusion research project. They calculate molecular collisions, and researchers have already ported code from OpenACC to OpenMP and made it work on both NVIDIA and AMD GPUs. Viscose is the last one. In this case, the group is using LAMPS with Cocos, and they have already contributed a patch to the LAMPS code base. And this concludes the presentation. Thank you for your attention.
Thank you, Ugo. I know I have a question from Benjamin that he wants to ask you. So Benjamin, go ahead and unmute yourself and ask away.
Yeah, great presentation, Ugo. So as Ugo pointed out, we're going to have a much faster CPU GPU memory connection, and there's cache coherency, which means that applications that you had to copy, you keep information on the GPU, you might not have to do that. But the weather and climate applications will still have to keep everything on the GPU, because not only has the host device bandwidth gone up, but the GPU device bandwidth has gone up by a lot as well. So it's all about this ratio and it's very application specific. There will be some applications that will benefit, but weather and climate, I'm afraid, data placement will still be very important. I think that's something to keep in mind.
Yes. Look, the issue here, and I did have other slides which I couldn't share because we did have a lot of NDA interaction, like you probably with AMD and the other side. The question is, you saw the C++ code before, and I was about to change it, adding that mmap to share a file with the GPU, but I didn't have time. So anyway, the thing is, the real question here is, what are we talking about here, right? If you look at the schematics for the Infinity Fabric, right, and the way they connect the GPU memory with the CPU memory, right? Is it GPU memory connected to the CPU chip itself with some cache in between, or what? I mean, it's hard to understand now, right? What you'd be able to do there, because indeed, once you have, I agree with you. So what I was thinking about when I said that, right, about hybrid code, CPU and GPU, specializing the kernels. So you have compute kernels running on the GPU, and you might have other kernels running on the CPU, which take care of the data movement and other things, right? This kind of processing, that's what I was thinking when I said that, right? We'll see. I don't know if you got access yourself already to some Infinity Fabric enabled hardware. I haven't, so we'll find out.
Let me know when you do.
We'll have a few chats in the future. Yeah.
Thank you, Benjamin, for the question. Ugo, that is the last question that we have. So thank you, and thank you again for Pawsey's support of this conference.
Yeah, no problem. Thanks a lot.